Bismillahirrahmanirrahim. Assalamualaikum warahmatullahi wabarakatuh. To my lecturer, Puan Zaidah binti Muhammad Noor, and my fellow friends. We are from CS2594A. We are now presenting abdominal and stomach pain detector. This is our development team, which is Amirul Hafif bin Johan, me as a project manager, and Muhammad Samir bin Marzuki as our programmer, Muhammad Nazmi Husaini bin Razman as our programmer too, and finally Muhammad Iqbal bin Mazri as our knowledge engineer. This is our table of content. For introduction, we are doing this project in terms of medical diagnostics, which is our domain, focus on the pain detection for stomach and abdominal pain. The difficulty of detecting pain for stomach and abdominal pain can be a huge hassle because the patient is usually interpret their pain differently from what the expert in medical field could understand. The reason of this is because the detection can be indistinct, blurred, and probably has vague symptoms. The problem statement is that there are a lot of difficulty in grading differentiation for every pain detection, even though there are a lot of involvement in diagnostic method using chemical, technical apparatus, medical history reference, and any examination which has been specialized. So our objective of our project is to develop a system that will ease the process of stomach and abdominal pain detection for users and experts. Our input include three things, which is pain scale, visual exam, urinalysis, days of pain, and the output as abdominal and stomach pain. Although our fuzzy system does not directly diagnose the user's disease, but the pain result can somehow predict the disease that they might possess. So the result of the abdominal pain has five, which is negligible, minor, moderate, major, and life-threatening. Negligible, which is something that we can often brush off, such as stomachache and or eating too much. And meanwhile, minor is something like lactose intolerance and gastroenteritis. And while moderate is like bloating, constipation, food poisoning, and something a disease that is almost the same like that. And meanwhile, the major include kidney stones, diarrhea, period pain, gastroesophageal reflux disease, which is GERD, or appendix. This is all the disease that kind of dangerous but not as much as life-threatening, but still very dangerous to us. And finally, life-threatening, which is the stage 4 colon cancer, peptic ulcer, or kwashiorkor. This is very um, dangerous and very harmful to us. So we are putting this based on our research and our domain expert. This is life-threatening. So now we are moving on to knowledge representation.
Okay, for the knowledge representation, we use the semantic network technique to represent our knowledge. So as you can see here, the center is our main output, which is the abdomen and stomach pain. So you can see here the pain scale bunch from the abdomen and stomach pain, and it has its own scale, which is no pain, mild, moderate, severe, worse pain. Same as days of pain and visual exam urinalysis. So the color for you visual exam urinalysis is clear, like clear yellow, dark yellow, brownish, and red. So for the days of pain, we have few which is less than 3 days, some which between 3 and 9 days, and many days which is above 9 days. So for the linguistic variable and values, we have five linguistic values for the input variable pain scale, which is no pain, mild, moderate, severe, worse pain. The numerical value is 0 to 1 for no pain, 1 to 3 for mild, 3 to 5 for moderate, severe, 5 to 9, and worse pain, 9 to 10. And the fuzzy value, we convert it to 0 to the point value. So for the input variable visual exam urinalysis, we have the linguistic value, which is clear yellow, dark yellow, brownish, right? So the fuzzy value, we get it from our article and our findings, and so we convert it to the fuzzy value that easier to make in our coding in future. So for the days of pain, we have few, some, many. The numerical value between 3 to 14, 14. And our output is abdominal and stomach pain. We have negligible, minor, moderate, major, life-threatening. So the fuzzy value is 0 to 0.2, 0.2 to 0.4, 0.4 to 0.6, 0.6 to 0.8, and 0.8 to 1. So proceed. So for the graph representation, we use Fuzzy System Development Platform MATLAB Fuzzy Logic Toolbox membership to membership function plot. So as you can see here, the first graph representation is for the pain scale graph. So we use the triangular method to create our graph. So as you can see here, our fuzzy graph for the pain scale. Next. So we also use all the fuzzy graph, triangular fuzzy graph for the visual exam analysis. So next. So same as the for the days of pain. So next, and same also for the abdominal and stomach pain. So that's all for one more for the fuzzy rows. We sample the 15 rows out of the 65 rows because it is too much to put it all here. So as you can see here, we use the rule 1. If pain scale is no pain and visual examination is clear, then abdominal and stomach pain is negligible. So you can compare it from the rule 1 and rule 10. So for the pain scale no pain, they have no days of pain because if you feel no pain, then how can you have a day of pain, right? So we have our control method on our system demo part. So this is our rule. So yeah, next. This is all our rule. So that's all from me.
Okay, this is for our inference system. For presentation purposes, we decided to use a sample where this is our sample right now, the input where the pain scale is 2, also known as mild. The visual exam urinalysis is 0.2, clear, and the days of pain is some for 9 days. And the output as the system being produced are 0.241757, and the result would be they have a minor stomach, abdominal and stomach pain. So moving on, next, we decided to use Mamdani style inference technique instead of Takagi Sugeno style because it fits our system much better. So this project includes the inference system includes the first step, fuzzification, rule evaluation, aggregation of the rule outputs, and last but not least, defuzzification. So moving to our first step, fuzzification. In our inference system, we did a fuzzification, as you already know, to transform crisp value into fuzzy values. So we can evaluate these values and see where it belongs to the appropriate fuzzy variables. So as we already know, this is for the first input, sample input, where the pain scale is 2. As you can see that the fuzzy variables are mild. And if you can see that, we decided to use the straight line formula, y equals mx plus t, to see the degrees of membership for the input pain scale 2. So right there from here, you can see the dotted line, and it shows that when the fuzzy variables is mild, the degree of membership is 0.9. So next, this is pretty much similar to the first, the previous slide. So for visual urinalysis, there's 0.2. As you can see there, we have an intercept for 2 different types of fuzzy variables for clear and yellow. And considering the degree of membership for clear is 0.1 and 0.3, and we are looking for the clear fuzzy variable as 0.2 belongs to the clear part, so we decided to take 0.1 as the degrees of membership. Next, this is for the days of pain, 9 days. So 9 days is considered as some days. So from the dotted line, as you can see there, 9 days, it hits the some fuzzy variables, and now we can see a corresponding y value, or the degree of membership, is 0.85. So that is pretty much the fuzzification method. So moving on, we have the rule evaluation. So all the fuzzified input values we are trying to make sure it corresponds to the rule antecedents, which we both use and or operator to generate a single output number for the fuzzy rules, which has multiple antecedents. So as you can see that if the rules has a and fuzzy operation, we will use that formula, the main formula for mu ax and mu bx. If it's an or fuzzy operation, then we'll be using a max between the mu of ax and the mu of bx. However, in this sample, we do not use or, since the rule that we does not contain or. The sample 1 is actually from the rule 11. As you can see that if pain scale is mild, 0.9, and the visual exam urinalysis is clear, 0.2, days of pain are some, 0.5, then abdominal stomach pain is negligible. Do inform that the numbers in the parentheses are all degrees of membership that we require from fuzzification. So as you can see that mu there mild is 0.9, mu for clear is 0.1, and mu for days of pain is 0.85. Consider that all of it is the rules uses an AND operation for all of it. So we decide we use min operation, min between 0.9, 0.2, 0.5, and the most lowest number is 0.2. Therefore, mu for abdominal stomach pain negligible is 0.2. So next we have the third step, aggregation. So based on sample 1, actually we need to unify the outputs from all rules and make into a single fuzzy set, and these membership functions for all rule consequences are being combined. Consider we decide to show only one sample, and this is what happens when you start with only a sample. We clip the graph to where the mu value for the previous rule antecedent, the previous rule, and since the value is 0.2, so it's we clip it only at the 0.2 and on the negligible part only. So next, the final step for our inference system is defuzzification. So from our sample 1 inputs, we generate a numerical value from all transform output, and applying the COG, center of gravity technique, in our calculation to determine the middle of the graph. And consider we have again only one sample, we only show it for the part of the negligible graph side. So as you can see there, the pain scale 2 mile, visual examiner analysis 0.2 clear, days of pain 9 sum, and the formula is COG. We take in all the x value for the part for the negligible only, 0 to 0.2, times the mu for the negligible abdominal and stomach pain, 0.2, divided for the value of all the mu, 0.2, and therefore we have the value 0.1, which is the middle point or at the center of gravity of the negligible part of the graph. So that's pretty much a conclusion towards it. We can deduce a conclusion that the user must probably have a negligible abdominal or stomach pain based on the input gathered. So this is pretty much a short summary for the center of gravity graph that includes every inputs for our rules from mild, clear, yellow, depending on which input that we decided to put. So as you can see there, there's a red line that determines where are the center of the gravity for each graph, and the shaded region represents where the graph has been clipped. And that is all for the inference system.
So this is our summary of our project, the fuzzy logic, which can be used to simplify abdominal and stomach pain detection. And secondly, by using method in fuzzy logic, it is acceptable value within predicted range for abdominal and stomach pain detection can be achieved. And finally, detecting abdominal and stomach pain can be done by applying the Mamdani style inference technique.
Okay, thank you, Amirul. Okay, now I'm going to explain the system demo that we are created using Fuzzy Logic Designer in MATLAB. The first thing we have to do is using the fuzzy command, which is inserted the input into our Fuzzy Logic Designer, and then use the rule editor inside the Fuzzy Logic Designer using the rule that we have discussed with our knowledge engineer and our domain expert. As you can see in the slide, that is our sample for Fuzzy Logic Designer and our rule. Now let's see our demonstration for our fuzzy system. Okay, now we are going to see in our MATLAB that we run our graphic user interface. So here is our system demo, which is called Fuzzy System Abdominal and Stomach Pain. Below the title, we have some command which say for pain scale in 0 to 10 range and visual exam urinalysis 0 until 1 and days of pain 0 until 20. This information is important because if the user inputs more than that range or lower than that range, it will give an error, or not an error, it will give some statement to say that the user has put a wrong number. So here is an example. In scale we use 11, and as you can see, the upper result told us to recheck our pain scale, which is not in the range. Now we are going to put it in our range for an example, and 1 and days of pain we are going to put 20. So here is our result, which is say output 0.912586. The result is called life-threatening, which is true based on our rule. And then the next example we're going to do is we're going to put a little bit of pain, and then half of the visual exam analysis, and days of pain we're going to put around 5. Now we're going to see it said minor, which is sorry. Yes, it said minor. Sorry. I got distracted below because there's a new feature in MATLAB, but it's okay. Our system demo work correctly. Now we're going to put pain scale 8, and then visual exam analysis 8. Oh, the system told us to recheck our input 2, which is of course we have to check because it's above 1, and then we put 0.8 also, and then yes. As you can see, the output is 0.7, which the result is major for the abdominal and stomach pain. This is an example for our system demo. Thank you.